These are the notes for AP Calculus on the topic of graphing functions using tables of data. So let's review some of the tools for graphing that you've learned in your previous math classes as well as this math class. So some of the tools are x and y intercepts, domain and range, symmetry, even and odd functions. Those are all useful tools that tell you something about the graph. Those are primarily from previous math classes leading up to calculus, and we also reviewed those, remember, in the prerequisite chapter. Then, discontinuities, holes and vertical asymptotes, limits and infinity, horizontal asymptotes. Those tell us all the things that are helpful about graphing. And those we went over in chapter 1. And now, in our current chapter, we've been focusing on relative extrema, for using the first derivative, and increasing and decreasing intervals using the first derivative test, as well as points of inflection and concave up and concave down intervals using the second derivative test. So these are the 4 things we're going to concentrate on in helping us graph functions using tables of data. So let's review the different types of intervals that we can have. If the first derivative is greater than 0 or positive, that must mean the original function is increasing. And if the second derivative is less than 0, that must mean the original function is concave down. So right here below this, let's draw what it looks like, and it's going to be increasing concave down, shaped like a frown. So increasing and decreasing always refers from left to right. So increasing concave down looks something like that. So concave down. And then if the first derivative is less than 0, that means the original function is decreasing. If the second derivative is less than 0, it's concave down. So decreasing concave down, shaped like a frown, look like that. But if the first derivative is less than 0, right here it's decreasing. If the second derivative is greater than 0, it's concave up. So decreasing concave up, shaped like a cup, would look like this. And if the first derivative is greater than 0, increasing. Second derivative greater than 0, concave up. So increasing concave up, shaped like a cup. The other half of the cup like that. So you can see if it's not linear, if it's concave up or concave down, these are the 4 ways the graph could look. And notice I've organized it this way because that's really just like you divide a circle up into 4 segments, into 4 curves, I should say. It's the different ways the graph could look. Now, obviously, it's not always going to be the same steepness, but this is still usually the rough shape of what a graph could look like. So now let's put this together with our table here and see if we can sketch this graph. So it says sketch the graph of a function having indicated characteristics. F of x is continuous on negative 10 to infinity. And it should also say in the instructions, left it off here, that to label all relative extrema, so our relative mins and maxes, and inflection points. Okay, so we'll label those once we're finished graphing. All right, so let's look at what a table gives us. On the first row, we've got x and then different ranges for the x coordinates, as well as some specific x coordinates. The second row is our f of x. That tells us our y values. A third row is f prime of x. That tells us the slope. And the fourth row is f double prime of x. That tells us about the concavity. So let's first figure out if we know any points for certain on this graph that have to be on the graph. Well, if we take a look here, we can see, and when x is negative 4, the y coordinate is 5. So negative 4, 5 would have to be on our graph. We can plot that point right here. Again, that's because this f of x row, this represents the y values. And we have another pointer when x is 0, the y coordinate is also 0, so it goes through 0, 0. Also goes through 2, negative 3. There. And 5, 0. So those are 4 points we know for certain this graph has to go to. So those are kind of the guideposts as we go along our graph here. Then, let's see what else we can figure out based on the first and second derivative. So the first derivative, being positive or negative, this will show us whether the original function is either increasing or decreasing. And the second derivative being positive or negative, that will tell us whether the original function is either concave down or concave up. Alright, so if the first derivative is positive, that must mean the original function is increasing, f of x is increasing. And if the second derivative is positive, it's concave up. Shaped like a cup. So, increasing concave up, increasing refers from left to right, and this is for x is less than -4. So all the way up until we reach this point here where x is -4. And notice the y values, it says, are positive as well, so it has to be up here. So if we want to draw an increasing concave up shaped like a cup, something like that. But if you leave it just like that, that's not going to be quite correct. Because if you leave it like that, that means eventually, these y values eventually are going to become negative at some point. Right? It just keeps getting lower and lower forever, even if it's really slow. So, but in our table it says they have to be positive. The only way we can avoid that, since it's continuous from negative infinity to infinity, is if we put a horizontal asymptote on the graph somewhere there. We don't know exactly where it is. It could actually be right on the x-axis. I would keep it positive. Or it could be somewhere positive like that. As long as it's somewhere there, now that will ensure that the y values never become negative and they stay positive. Then, right at -4, you can see the first derivative and second derivative don't exist. We'll see why that is once we graph this next interval. So the next one is from -4 to 0. So from this point to this point. And the first derivative is negative. That means f of x is decreasing. The second derivative is negative means f of x is concave down. So decreasing concave down, shaped like a frown. Something like this. Decreasing concave down. Until we get to that one. Now let's see, why was this doesn't exist? Well, notice we've got an abrupt change in the slope. We've got a corner there. That's why the first derivative doesn't exist. And if the first derivative doesn't exist, well, then the second derivative can't exist there either. Now let's look for the next interval from 0 to 2. Oh, notice the y values here are positive, right? These are all positive y values. From 0 to 2, from this point to this point, the first derivative is negative, so the graph is decreasing. The second derivative is positive, so the graph of f is concave up. So decreasing concave up, shaped like a cup until we get to this point. And notice the first derivative is 0 right there, so we want to level it off when we get there. So decreasing concave up, shaped like a cup. And let's look back at here at 0 and see if these make sense. Notice these are all negative, including right there, because the slope is negative that whole way there, right? It's decreasing the whole way. The second derivative is 0 because it switches concavity from concave down to concave up. We'll label those key points at the end. Now let's take a look at our next interval from 2 to 5. The first derivative is positive, means the graph is increasing. Second derivative is positive, concave up. So increasing concave up, shaped like a cup until we get to that point. And notice on both of these, the y values are negative, right? Both of these intervals. And notice right here, the first derivative is 0, because the slope, it levels off right there. And the second derivative is positive this whole way, because this whole thing is concave up. And then the last interval, where x is greater than 5, it's increasing, since the first derivative is positive. And second derivative is negative, so it's concave down, shaped like a frown. So here, increasing concave down, shaped like a frown, look like that. Careful not to draw that too far there. Don't get carried away and make it like that, because then it starts to decrease. Make sure it just keeps increasing. And notice on here, do you think we need a horizontal asymptote to keep it positive? In this case, it's going to stay positive on its own. So you could put a horizontal, so it wouldn't be wrong. It's just not necessary here. And notice here, the first derivative is positive at 5, because the slope here is positive, and the second derivative is 0, because it's switching concavity. So lastly, let's just label all the relative extrema and inflection points on our graph. So let's look for any relative maximums. Well, we've got one relative maximum where the first derivative changes from positive to negative. Right here, we can see it on our graph. That point right there is the relative maximum at -4, 5. And that's the only one. That's the only place the first derivative switches from positive to negative. Let's look for any relative minimums. You can see the first derivative switches from negative to positive at 2. You can see that on our graph right here. So this is our relative minimum. And that's the only one. That's the only place where the x where the first derivative switches from negative to positive. Now let's look for any points of inflection. That's when this graph changes concavity, the second derivative changes sign. So we've got a point of inflection right here at 0, second derivative changes sign, switches from concave down to concave up. Let's label that on the graph. And also at 5, it switches from concave up to concave down right there. That's a point of inflection. And there's actually one more, which may not be as obvious, but at this relative maximum, notice it switches from concave up to concave down. So since it switches sign there, that's also a point of inflection. So this point, that's partly what's causes this weird corner right there, is because it switches not only relative maximum, it also switches concavity at the same time, being point of inflection. And that concludes the notes for AP Calculus on the topic of graphing functions using tables of data.